on top of the Cartesian plane, right, and inside a circle, because we're studying this circular motion. So we have to learn a few new, just sort of a few new setups and layouts. Because our trig is going to be inside a circle, a special kind of circle, by the way, what we're interested in points that lie on the outside of the circle, that lie on the circumference. So we talk about these points, we just call them P, like representing point. And any point that we put on our xy coordinate system has an x and a y coordinate, right? So a point xy lies on the terminal arm of an angle in standard position. Okay? Last week you might not have been able to understand what that sentence means, right? But now I hope it does. A point, and every point has an xy coordinate, lies on the terminal arm of an angle in standard position. Okay, so here's my angle in standard position, right? This wasn't completely formed for you, but here's my angle in standard position, agree? And here it is, there's my angle. So, when we have a point in standard position, if we also have a circle drawn on the Cartesian plane, and this is going to be a special kind of circle. This is called the unit circle, and a unit circle has a radius of 1. But let's just not even talk about the unit circle. Let's just say we've got a perfect circle drawn. The center is at the origin, and I picked a point P that lies at the intersection of the circle and the terminal arm of the angle. So P lies on both of those things. Okay? So if the point lies 1 unit from the origin, we can use the Pythagorean theorem to relate the radius of the circle and the coordinates of P. So basically, what we've got is we've got a triangle embedded in a circle. Now this is a special circle because we've chosen a circle with radius of 1. Because it doesn't really, we kind of talked yesterday, it doesn't really matter how big I make the circle. One rotation of any size circle is 360 or 2 pi radians. So we may as well make the circle as small as we possibly can to make it nice to work with, right? So we're picking a circle of radius of 1. But these trig ratios could be used with any size circle, right? Okay. So what I did is I picked a point on the intersection of the circle and the terminal arm, and that point has coordinates x, y. Now, if I draw a triangle, so I took from the point P and I drew a perpendicular line to the x-axis, creating a right angle. Okay? That creates a right angle triangle. Can you see that? So this is how it started. I'll show you how it started before all those things were drawn. Right? So all you did, you had your Cartesian plane, you had your x and y axis. I'll draw the angle first. So I drew an angle in standard position, and I just picked a point. Okay? Now, this point, or actually what I should do is I'll do this first. Then we drew a circle. Whoa, that's a really bad circle. Okay, we drew a perfect circle, right? And this perfect circle had a center at the origin. Okay? So when this, and I picked the circle to have a radius of 1. So if the radius of 1 from here to here is a unit of 1, from here to here is a unit of 1, here to here is supposed to be 1, from here to here would also be 1 as well, right? Yeah. Okay? Now this point, I don't know the identity of the point, I'm just going to call it xy. But what I did is I took this point here at the end of the radius and I just dropped a perfect perpendicular line down for the third side of the triangle, and I made it be perpendicular so I knew I had a right angle there. Okay? That was all set up, drawn for you in your booklets. So we know it's a right angle triangle. Because we studied right angle triangles before, we know a lot about them. Okay. When I have this right angle triangle, I have the hypotenuse, right? That's the hypotenuse. This is the angle we're interested in. We're interested in the angle of rotation. So this is the important angle. Okay. Now, according to this angle, this side is called the opposite side, and this side is called the adjacent side. Agreed? So, according to our trig ratios then, the cosine of this angle is equal to adjacent over hype, right? Sine of the angle is op over hype, and tan is op over adjacent, right? That's what you know. That's your knowledge that you knew before, right? That you've picked up in prior classes. Okay, so now if I also, would you also agree with me that if I just, because I labeled this point x, y, and the coordinate of this point is x and y, that means the distance from here to here along the x-axis, right? This distance is what the value of my x-coordinate is, right? And this distance is the value of my y-coordinate, right? Good? Okay. So another way, I could call this the opposite side, but I could also refer to it as y, because I know its length is y, right? Because this y matches up with the y-coordinate on the y-axis. The x is whatever the x-coordinate on the x-axis. So this length is also the distance of x, okay? So instead of just saying adjacent op and op adjacent, I could also refer to cos as, okay, what is cos? It would be x over 1, right? Because the radius is 1, the hypotenuse is equal to 1. The sine is equal to y over 1, and tan is equal to y over x. Okay? That's why it's really nice picking a circle with radius of 1. It just simplifies our job. It doesn't change the angle measure, which is what we're really interested in. We're interested in the angle measure, but radius of 1 is super easy to work with, right? So now look what we have. On a circle with radius of 1, we can refer to x over 1. What would x over 1 simplify to? Just x. Y over 1 simplifies to just y. And tan, of course, has to stay y over x, right? Therefore, when a point P has coordinates x, y, and it lies on a circle with radius 1, we refer to this type of circle, we call it the unit circle. That word unit means 1, right? You know the word in French for 1? That's where that word comes from, right? Unit is 1. So the coordinates of P, so this is the really interesting thing. And if I go back up here for a sec, it talked about, this is your equation of the unit circle, right? The equation of a circle is, with the center at origin, is x squared plus y squared equals 1. Maybe I'll give this to you. The equation of any circle, we don't study, like we study circular motion, we don't study circles just shape in grade 12, but I think you should know this. This is the equation of a circle. Has anyone seen that before? Yeah. Where it's just a shape, right? They used to have a unit in grade 12 called conics where we studied things like this, but they took it out. XY is, oh sorry, not XY, HK. What does HK represent? I heard someone say that they'd seen this before. What do you think HK represents? In regards to the circle, though? No, it's the center. HK are the coordinates of the center. Okay, and what do you think R represents? Radius, because that's all you need to know to be able to draw or locate a circle. You need to know where the center is, right? Where to plot the center, and then what the radius is. As long as you have the radius, you can draw the circle, right? So, can you see that for the unit circle, can you see why it becomes just this? Because the unit circle, what's the center? The center is 0, 0, right? So it came from x minus 0 squared plus y minus 0 squared equals 1 squared. And that just simplifies to x squared plus y squared is 1. Okay. Yeah. Easy circle, right? The simplest circle you could get. So this is the big ta-da for this first part of today. Therefore, when a point P lies on the circle, like the circumference of a circle, the coordinates of P can also be expressed as cos theta sine theta instead of xy. Okay. So let's go back. See this P, the coordinates are xy. Yes, that's true. There's no disputing that. But we could also say the coordinates, as long as P is a point at the intersection of the terminal arm of the angle and the unit circle, we can say that cos, or the coordinates of P, I'm just substituting cos theta for x and sine theta for y, because that's what we just determined over here, right? Okay. The reason we want to call them cos theta sine theta is because that gives us so much more knowledge of what's happening at the point and with this angle than just referring to them as x and y. Okay? It gives us tons of knowledge. Okay, let's see what we're going to do over here. I also want to introduce you to the reciprocal trig functions. Sine, cos, and tan are called the primary trig functions. So note, sine theta, cos theta, and tan theta are called, they're the main guys, right? The primary trig functions, or trig ratios. Ratios or functions, either or, fine, okay? So the secondary ones are the reciprocals. And the reciprocal functions are secant, cosecant, and cotan. You won't see them written out in long form much, and I won't do that either. It just takes too much time. Just the same as sine, cos, and tan actually have longer names, right? Sine is actually S-I-N-E. This is actually co, S-I-N-E, and this is actually tangent. But we always just refer to them with 3 letters. One of the reasons, too, is so they'll all fit on your calculator buttons, right? So, because we don't have room on calculator buttons for big names. So secant is shortened to SEC. Cosecant is CSC. And cotan is just COT, okay? So cos and secant are reciprocals. Sine and cosecant are reciprocals, and tan and cotan. Meaning that secant, in this case, secant is 1 over x, right? Cosecant would be 1 over y, and cotan is x over y instead of y over x. Okay? So the coordinates of points on the unit circle can be used to identify trig ratios of angles terminating in quadrant 1. We can also use our knowledge of reference angles to find values for trig ratios in all 3 other quadrants. Okay? Any questions so far before we go on with this? Are we doing okay? So the big takeaway is every point that's on the circle and also on the terminal arm of an angle, we're not going to call the coordinates x, y anymore. We're going to call it cos theta sine theta. So let's see this. For each point x, y on the terminal arm of angle and standard position, so we know it's one of our special points, determine the 6 trig ratios for theta. To the nearest hundredth, determine possible values for theta. Okay, so they gave us the point 1, 4. So the first thing I would think is, I think I would kind of do a quick sketch here. So it sort of looks like that first example we saw. What quadrant is 1, 4? First quadrant, right? So it'd probably look like, I don't know. This is 1 and 4. Okay, so here's my point, right? Okay, so this is point P. It lies on the terminal arm of an angle in standard position. Okay? Now, the interesting thing is, this point is not on the unit circle, is it? I don't think it can be, right? Because this is way bigger than a radius of 1. But it doesn't really matter because we're talking about the trig ratios themselves, as long as we can get them developed, it doesn't really matter. This concept applies to any circle, right? Big or small. So we're just going to use this concept and see if we can come up with our trig ratios. So here's my point P. I'm going to drop my triangle, or drop my side to create my right angle triangle. And I'm going to identify where theta is. Because they said the point P lies on the terminal arm. So this is my angle. This is my angle that I was looking at. Okay? They just want the 6 trig ratios for theta. Okay, so what do I need? I need cos of theta, sine of theta, tan of theta. Because once again, the trig ratios, it doesn't really matter what size of circle they're cos of an angle, and the angle measure doesn't change no matter how big the circle is. So I'm going to do the reciprocals over here, right? I want secant theta, cosecant theta, and cotan theta. All right. So what do I need in order to come up with my cos, my sine, and tan? I need to know this length, right? Is 1. This side is 4, right? And how long is the radius then? The hypotenuse. Can we figure out how long the hypotenuse is? Let's see. What did you do? The hypotenuse equals 4 squared plus 1 squared. Sorry, the hypotenuse squared equals 17. So hype equals root 17. Perfect. Okay, so cos equals adjacent over hypotenuse, right? Sine equals op over hypotenuse, and tan equals op over adjacent, or just, I guess we could just say just 4 in this case, right? So what will secant equal? Yeah, so it would be just root 17, wouldn't it? Or root 17 over 1. This would be root 17 over 4. And this would be 1 over 4. That's it. That's all we're doing. We're just establishing the ratios. Okay, so this isn't the unit circle. It's not one of our special circles. So cos isn't just equal to x, right? It's equal to the adjacent over the hypotenuse. What do we have to do now? So we determined the 6 trig ratios for theta. Okay, to the nearest 100th, determine possible values for theta in the given domain. Okay, so they just said, I know this point is in quadrant 1. Since P lies in quadrant 1, okay, I know that it lies in quadrant 1, so they didn't give me, I don't have to do any more. The only angle I'm interested in is this one. Okay, there are no related angles that satisfy this information because they told me it terminates in quadrant 1. So I'm just looking for quadrant 1 angle. Okay, theta lies in quadrant 1 also. Okay, so how do I figure out what theta is? Yeah. So which ratio do you want to use to inverse to find what theta is? Do you want to use cos, sine, or tan? Okay, since tan theta equals 4, theta equals, okay, you need your calculator. Now it's asking in degrees, right? So make sure you're in degrees. And it said to the 100th, right? So theta equals 75.96 degrees. Agree? What if you wanted to use cos instead? What would you do? Shift cos, 1 divided by root 17, right? Shift cos, 1 divided by root 17. Let's see what that gives us. Whoops, that should work. Same answer, right? It doesn't matter which ratio you pick. Shift sign, 4 divided by root 17. Same answer, right? It absolutely does. You shouldn't get different answers, right? It's all talking about the same angle. The only ones why wouldn't I pick secant, cosecant, or cotan, do you think? I don't have those buttons, right? I only have sine, cos, and tan. Okay? Yeah? Okay, what about, because they gave me a point, I know it's in quadrant 1. Right? I don't, there's no other, I could have searched these other 4 quadrants, but they told me it was in quadrant 1, so I only have one answer for theta. What about this one? Point P, which is -3, -5, over the domain 0 to 2 pi, so they want me to do it in radians this time. Okay. Try this one. So what quadrant will this one be in? Yeah. So it's going to be here. Here's my P, right? So this is interesting because here's where my theta is, right? Agreed? But how do I draw a triangle with an obtuse angle like this? I can't draw a right angle triangle, right? Doesn't make sense because this is where my theta is. So in this case, what we learned kind of yesterday is you've got 4 or 3 other related angles to your reference angle, right? So because reference angles give the same trig values as related angles, I don't have to worry that my angle created is actually obtuse and it covers 3 quadrants. I can just draw my right angle triangle, okay, and I can use the reference angle, if that makes sense, okay. The reference angle will give me the same value. That's why they're all related. So I don't really have to worry about theta yet. I'll worry about theta at the end when I have in part 2 where I have to solve for theta. But for now, I know that this triangle is going to hold the same information as a triangle with the same reference angle in quadrant 2 or quadrant 1. So let's just go along, and so the angle's at the center of rotation again. I always connect my triangle to the x-axis, creating a right angled triangle. So what do I have here? I have this distance is 3. This distance is 5. Okay, so now I just have to find my hypotenuse. And I'm going to start calling my hypotenuse r, because it's actually the radius of a circle, right? This P is actually lying on a circle too, so I'm just going to call my radius r. So 3 squared plus 5 squared equals r squared, right? I think 34 equals r squared. Yeah? Okay, so here we go. Cos of the angle, sine of the angle, tan of the angle, secant, cosecant, cotan. Okay, be very I'm going to get you to set up the ratios. I'm going to caution you to be careful though. gonna get you guys to go for break too. Okay, what did you get for cos theta? What's the ratio for cos? Adjacent over hypotenuse, right? So x over r. -3 over root 34. Agreed? Okay. Remember that even though when you're finding the lengths of a triangle, lengths are always positive, your x value is negative, right? Your y value is negative. And in quadrant 3, cosine are negative, only tan is positive, right? So sine would be -5 over root 34. And tan is 5/3, right? Okay, so cotan is 3/5. Cosecant is negative root 34 over 5. And secant is negative root 34 over 3. It doesn't matter where the negative sign goes, it just belongs to the whole fraction. And notice that in grade 12, you don't have to rationalize when you have root signs in the denominators. That's kind of nice. Okay, I didn't have to worry about finding any related angles. I just had to find the angle in this quadrant 3. But what I would suggest you doing is always find the related angle first and then figure out what quadrant you're in. So it doesn't matter again which tree. I think I'll probably use tan again, right? So shift tan, 5 divided by 3. It's the easiest. So the related angle is equal to 2. And I'd always suggest you use related angles. The only reason I didn't use it here is because it was quadrant 1. Okay, so I get 59.04 degrees. Okay, but that's my quadrant 1 angle. So in quadrant 3, what's my angle measure going to be? (180 plus 59.04 plus 59. Yeah, 239.04 degrees.
Was it you want to find quadrant 2?
Well, because it was in quadrant 3, right?
Yeah.
Okay, take a break.